All right, I'm going to show you how to do parts B and C on a question like this. First of all, it's asking you to find the area between 1 and 5. That's the ultimate goal here. Now, part D, you may have seen from other videos and from other exercises. To express the answer area that we're looking for as an integral, that would be this thing down here. And we would just stick the function in here. We would put dx or delta x to remind us what variable we are dealing with here. But the red thing there, that's the integral symbol. So part D, that's how you would express that function as an integral from 1 to 5. And then, of course, E, you're going to use a graphing calculator or Desmos or some other technology to find the answer. Now, part A here is to graph that. So we have on the right here in the lower right hand of your screen, we have a red parabola, x squared, and I have marked off from 2 to 6 because I'm going to do this example from 2 to 6, even though the directions for this particular question has from 1 to 5. You're just going to have a different upper and lower bound, but I'm going to actually be doing from 2 to 6, so 2 to 6. What we are interested in is finding the area underneath the curve above the x-axis. Here's the x-axis, and here's the curve. So it's trapped between 2 and 6. Now notice the shape here. There is no name for this shape in a geometry textbook. If you look this up in the back, it looks trapezoidal, but the problem is this side here is curvy. You know, this yellow side, it's not a trapezoid, and it's not a semicircle or a quarter circle. It's a very, very unique shape, okay? So you're being asked to find the area of a shape that really has no name, okay? It has no name. Now, to give you a little bit of context and history to this, before I explain to you how to do parts B and C, a little bit of history here because I want you to understand the concept, not just how to get the answer, because that's just what I do. Now, in Algebra 1, you guys learned a lot about slope, and in calculus, we call it the derivative, okay? So the derivative is finding the slope of non-straight lines. Like, for example, the bottom, this parabola here is curvy. In Algebra 1, you never found the slope of a curvy line. What calculus does is it allows you, using derivatives, to find the slope of the tangent line as it moves along a curve, okay? So the slope is changing. Over here, the slope would be negative because it's going downhill. Over here, the slope would be positive because it's going uphill, and the slope is changing. Now, the shortcut to find the derivative is the power rule, and I'm sure you love the power rule the first time you saw it. You're like, wow, this is fantastic. The long way to do it is using the h-limit, okay? Now, what slope is to derivative, area is to integrals. Area is a very basic concept you learned in elementary school, in geometry and algebra 1. You found the area of rectangles, squares, rhombi, things like that. But what about the shape like I just talked about, this wedgie shape that looks like a quarter pipe of a skateboard ramp? So what slope is to derivatives, area is to integrals. Integrals allow you to find the area of non-traditional figures, okay? Now the shortcut to that is to do the antiderivative. Well, the ultimate shortcut is to just use a graphing calculator. But there is a way to do it by hand using the antiderivative, and in this video I'm not going to show you how to do that. In one of my previous videos that you may have seen, I showed you how to find the area using the antiderivative, which is just undoing the power rule. It's the power rule in reverse. Now, the long way to do it, which is what this math Excel question is asking you to do, is to use what's called a Riemann sum. I like to call them Riemann rectangles, okay? So Riemann is a mathematician that had a brilliant idea. It's a theoretical and complex, but there's also simplicity in it as well, and I would like to show you a Riemann sum. And then I'll get back to answering the question, okay? So allow me to give a little bit of history and nerd out with you a little bit here. So first of all, whenever you're doing the integral, we're trying to find the first one here. This is f of x, that's the given function. It's some random curve. And the lower bound is a, and the upper bound is b. So our ultimate goal is to find the area of this peach stuff. That is our goal. The problem is there is no area for that peach thing. It doesn't have a name. However, if you break up the bottom as little rectangles here, as in the star graph here, if you put rectangles that have the same width, let's just say the width of 1, okay? The heights of the rectangles are different, like this height of this rectangle is taller than the height of this rectangle, but they're all the same width. So what Riemann did is he says, let's find the area of a bunch of rectangles under the curve. It will be an approximation, because as you can see in the top here, when you're dealing with rectangles, you're going to have a little bit of error here. So these little peach things, that is the area that's not included here. If you add up the area of the purple rectangles, it would be a good approximation of the whole peach. It's going to underestimate because the area is below, okay? In the graph on the far right, as you can see, the rectangles go outside of the curve. So this area would overestimate the true area. But what Riemann said is that if you have rectangles, if you change the width of the rectangles, let's say instead of 1, suppose we have the width of the rectangle of 0.01, okay? Which means the skinnier the rectangle is, the smaller the error is going to be. See this little green thing in the upper right? That is a pretty large error of area. It overestimates the area. So what Riemann said is, let's take the area of a bunch of little baby rectangles. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles. Suppose you take a curve and you break it up into 32 rectangles, okay? So more rectangles. So suppose the width of this rectangle is 0.01, the width of that rectangle is 0.01. So what you'd be adding up is you'd be adding up 32 rectangles that have the same width. And as you can see, the more rectangles you have, the smaller the error is, okay? So more rectangles means more accurate area, which means less error, okay? So believe it or not, when you do an integral here, you're adding up the area of a gazillion rectangles that have a width of like a micron, okay? So that's the history behind it. Let's get back to reality here. So part B here, 4 subintervals. Now I want you to notice between 1 and 5, the distance of that is 4, okay? Between 2 and 6, the distance between 2 and 6 is also 4. If I have to break this up into 4 rectangles, 4 subrectangles, that would mean that the width of the rectangle would be 1, okay? I have a larger picture of this. So here we have the parabola, x squared, and I want to find the area between 2 and 6, okay? Between 2 and 6, so as you can see, width of 1, width of 1, width of 1, width of 1. The area I'm looking for is the area of rectangles A plus B plus C plus D. What's the area of a rectangle? Length times width. What is the width of all 4 of these rectangles? 1. So the area of rectangle 1 has a width of 1. The area of rectangle B has a width of 1. The area of rectangle C has a width of area, the width is 1 and D is also 1. So the beauty of a Riemann sum is you're really just adding up the area of rectangles of the same width, okay? In this case, they want you to do subintervals of 4 subintervals between 1 and 5. That just means you're adding up 4 rectangles of width of 1. I'm doing it from 2 to 6. This is 1 to 5. It still has a distance of 4, So these subintervals are also going to be the width of 1. Now the question is, what is the height of these rectangles? Okay, so the area of a rectangle is length times width. I have the width of 1, width of 1, width of 1, width of 1. I need to know the length. In this case, that's the height. It's that pink line there. 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 So in other words, the height of these rectangles is a point on the green curve. The green curve is x squared. So all I have to do is plug in the x value into the function. Let me use a dark color here. I'm going to take the x value of 2 and plug that in here. 2 squared is 4. That means the height of this point is 4, and that's also the height of that rectangle. I'm going to put that down here at 4. And what about this one? How tall is that? Well, that is at the x value of 3. If I plug in 3, 3 squared is 9. Okay, that's the height of this point here on the y-axis, 9. This is at 4. So the y value is also the height of the rectangle, or the length of the rectangle. So this is 9. This right here is 4 squared, which is 16. And the last one is 5 squared, which is 25. So the area under the curve between 2 and 6 is 4 plus 9 plus 16 plus 25. That's the overall answer. And once again, it's just an estimation. I don't even know what the number is. I'm not going to take the time to figure that out. That is just an estimation because as you can see, there's going to be amount of error. If you look at the yellow here, I'm underestimating the true area because these are rectangles. There's a gap there. Okay? So that's what you would do for part B on this question, is you'd break it up into 4 rectangles, and the height of the rectangle, you're going to plug in the x value into the original function to get the height. Now, the harder part, and actually the Riemann sums are not necessarily difficult, they're just tedious. This is tedious. You're adding up the area of rectangles. If you look at C, this one says 8 subintervals between 1 and 5. So I'm going to draw a quick picture of that at the very end here. So between 2 and 5, here's 2, here's 5. Okay. Now we want subintervals of distance. We want 8 intervals, 8 intervals or 8 rectangles, which means that the distance has to be 1, 2, 3, 4, 5, 6. Okay, make believe all these rectangles have the same width. Here's 1, 2, 3, 4, 5, 6, 7. Let's sneak in one more. 8. Okay? So we have 8 intervals, which means that the distance of the rectangles has to be a change of 5 or 0.05 units. 0.05, 0.05, 0.05, which means that the x values at the bottom of the rectangle, I'm talking really fast here because I'm assuming you're following me here. So that means that x value here is at 2.5. This x value here is at 3 because I'm adding 0.5 units. Back up here, I got a quick boo-boo here. This is 0.5. 0.5, just like I have it here. Not 0.05, but 0.5, which is really a half a unit, which means that this unit here is going to be 4.5, and then I end up at 5. So you're going to be doing the same thing here. You're going to be breaking it up into the Riemann sums. You're going to have 8 rectangles that you're going to add. The area of each rectangle, the width of each rectangle is going to be a half a unit. The height is going to be the function value of those. So in this case, it would be 2.5, 3, 3.5, 4, 4.5, 5, 5.5, excuse me, 4.5 and 5. And you're going to add up 8 rectangles. All of them have the same width of 0.5, but the height is going to be different for each one. And if you followed me on this picture here, instead of having whole numbers, since you're plugging in like numbers like 2.5, when you square 2.5, you're going to get 6.25. So the area of the rectangles are going to be really ugly to work